All right. People in the back hear me well? All right, good. All right, yeah. Thank you very much for the invitation to this very nice place. I've sent lots of pictures from this area, and everyone thinks I'm in south of France. It's a wonderful place. And of course, the meeting, it's a great opportunity to meet so many people from different areas. It's supposed to be a spin workshop. I was quite afraid that I would be the only one not talking about spins, but in the meantime, I've seen that several of other people have given a spin-free talk, so I feel free to also talk about the stuff that we're doing. There'll be one slide that is a little magnetic, but otherwise, it's kind of magnetic field-free type of presentation. See if this works. Of course, it doesn't. Let's see. The laser works. Or it doesn't. Okay, I'll just do the manual thing. It might be that it's my port, but then it should work. Just get rid of that. There we go. Yeah, thank you very much. So the people who are currently in this part of the group where we do quantum optics at the nanoscale are Stefan Götzinger, Tobias Hubdiker, and Jan Renger, who have permanent positions, and then we have postdocs and PhD students. Mohammed is somewhere here in the audience. I'm going to tell you about molecules. Claudio already advertised molecules to some extent, more from a theoretical point of view, and I'm going to give you a talk that is all going to be on molecules and hopefully you will get kind of familiarized with the system. Typically, when people list their quantum emitters, they don't think about the molecules, but I'll try to convince you that they are doing quite well for many of the things that you do with your other quantum emitters. When we talk about molecules, we're talking about a solid state type of system. So we're going to have molecules that would be, I call them guest molecules or impurities that will be embedded in an organic host. This type of molecules, I mean, for physicists, they all kind of look similar, and to some extent, they are. The difference is that these guys, as you see, they're a little bigger, and by the logic of a particle in a box, the transition in these things is more in the visible, and the transition, the band gap in this, the host one, is in the UV, so the host is basically working like a dielectric that doesn't see the light that we're going to send. And you see that the chemist can put these rings in little different places, and by doing that, you get a certain functionality in terms of the wavelength. You can tune these molecules anywhere between 400 and such nanometers up to almost 800, and there's almost a one-to-one correspondence between alkali atoms that you might like and a certain molecule that we can work with. This is a kind of a pretty old system. It's been known for several decades. What's special about this combination is that when you go to temperatures below 2 Kelvin or so, the transition, the homogeneous transition of these guest molecules becomes as narrow as the natural line width. That is, if you look at the line width that we measured, and I'll show you a little more about that in a second, this, first of all, is in the same order of magnitude as you would have from an alkali atom in vacuum. But more importantly, for a solid-state system, it is Fourier limited. That is, if you were to measure the lifetime, you would get basically 1/2 pi of that. This makes these systems extremely bright emitters. One thing that you have to kind of just get in your head is that these molecules do not bleach. So if you've ever come across a talk where molecules were bleaching, this is not this type of system. We can work with the same molecule for 2 years, and usually something happens that we just throw that molecule away, but the molecule does not bleach. Now, there's actually a new kind of, let's say, a group of experiments that many other groups are also doing. The work, for example, in Chicago, the work in Paris, in particular combining organics and metal ions. The one that I'm going to tell you about is pure organic. So overall, using molecules for kind of quantum optical functionality is taking a little more kind of momentum. Okay, so when we put a molecule in a crystal, of course, as usual, as you know from color centers or quantum dots, you know that there's an inhomogeneous distribution of the energies because your crystal is never perfect, and each molecule is going to see a slightly different environment, and that is the key to detecting these molecules. That is, we detect single molecules in frequency space primarily. If you scan your laser across the inhomogeneous band, you see that at temperatures below 2 Kelvin, you see lots of sharp lines, and each one of those corresponds to one of these molecules that you see in the matrix. If you were to zoom into one of these resonances, then you see the Lorentzian shape that I just showed you. And this happens to be, again, a Fourier-limited line. So although you have a matrix, the combination of the molecule and the matrix is such that you don't have any phonon coupling. And what you see here is the so-called zero phonon transition. All right. Now I'm going to show you one example of how you can use this very fine resonance in a way as a sensor. This has been shown in this community for a few decades. You know, the molecules react to pressure, they react to electric fields. These molecules do not have spins in the ground state because they're neutral molecules. All the electrons are paired, and but they can be a very, very good sensor of electric fields. So I'm just going to give you a quick example of that from a recent work. In this work, we had a gallium phosphide waveguide, but think of this essentially as a gallium phosphide nanostructure. And then we put molecules surrounding it. And in more detail, this is kind of the structure. We have this waveguide. We can couple light into the waveguide, and we can couple light out of the waveguide. We also have microelectrodes around them so that we can apply an electric field. Not that important for this work. But if you were to then look at the molecules that are coupling to this waveguide, you see that there are a whole bunch of molecules along the way that are coupling to this waveguide. And now, a little bit similar to what Natalie told you about the kind of sensing magnetic noise or magnetic fields, what we are doing here is we're using two molecules that are sitting very close to each other, and we can look at the shift of the start shift of these molecules, or the fluctuations of the start shift of these molecules, to measure correlation in the noise, that electric noise that we have. And this noise, without going through detail, happens to be the kind of electric noise that has to do with charge fluctuations in this gallium phosphide. There is another molecule far away, and that molecule, for example, is too far to see this. So you see here, this is time scale in kind of a slow time scale. You see how the resonance of molecule 1 and molecule 2, they're going up and down together. So these are close enough to see the same electric field, whereas the resonance of the third molecule is not correlated with that. And again, also here, you know, if we look at do something like a cross correlation, you clearly see that these two are correlated, and one of them with the other one is not. So, so in that work, we could do analysis and see that the number of charges that are leading to this fluctuation is really something that is beginning to be grainy. That is, we have something of the order of tens of charges that are at work. And in principle, if you had a sample that had only one charge, we would have the sensitivity of measuring that as well. Okay, but the main part of my talk is to see how, after decades of doing single molecule, single photon type of work, how we can scale up and do more of a kind of what everyone else is doing, cooperative type of study. And the idea would be to have a network of a whole bunch of molecules and a whole bunch of photons with the aim of controlling each one of these nodes on the photon level and on the quantum emitter level. So that's kind of like a big goal to have, especially when you're doing cryogenic work and all of that. But that's kind of what we think would be interesting to do. Now, in a way, many, many years ago, more than 20 years ago, we had the first go at this when we looked at two molecules that were very close to each other. So these two molecules happened to be at a distance of only about 10 nanometers from each other. And we could observe and study in great detail the dipole-dipole coupling that they experienced. And in a way, with all the discussion that we've had in the past couple of days, I thought that I would show this again. So this is a kind of a textbook case of having molecule 1, molecule 2. Remember that because they are all slightly sitting at different sites, they don't have the same energy. They have a slight detuning with respect to each other. So that's why this one has a lower energy than this one. But if they come very close to each other, nevertheless, they undergo dipole-dipole coupling, which would be given by this simple interaction. And then, of course, when you write your interaction matrix, you would see that you get two new energy levels, which are the hybridization of these two other ones. But then you also have a doubly excited state. And we could do a spectroscopy and see all of that. And this is an example of the kind of a curve that you would record. You see that the lower energy one is your subradiant state, and the other one is the superradiant. You see here is that the subradiant is not completely, hasn't gone all the way to zero because we had a finite detuning between the two molecules, but you clearly see the subradiant and superradiant state. And then in the middle, you can have a two-photon excitation going all the way to excite the system in a doubly excited way. So just to show that this was kind of many years ago, unfortunately, it's very difficult to put two molecules at will at whatever distance you want over a few nanometers. We're going at this again via chemistry now, try to just make molecules that are linked in a certain way. That's a difficult thing, and of course we're not chemists, so we're collaborating on that. We'll see how far that goes. But from a physics point of view, that's kind of difficult. Nevertheless, more recently, and this is kind of the magnetic thing that I want to show you, it's a theoretical proposal, a little bit of a dreamy thing. And it's motivated by the work that has been done in metamaterials, so in the classical optics type of thing. So over the past 10, 15 years, lots of people have shown that if you have something like a split ring resonator, you can get magnetic activity at optical frequencies. Basically, you can think that you get an electric current going through here, and then that creates a magnetic field that goes out of the page. And we thought that actually what I just showed you can be used to do the same thing, because if you look at the subradiant and the superradiant case, you can think of this as two dipoles that are parallel or two dipoles that are anti-parallel to each other. And now if you look at the dipoles in a way as a kind of a current that is going through, right, then you would see that in one case, the magnetic fields created by each one of these currents is going to add up, and in the other case, they're going to cancel. And so in this case, you would have no magnetic field. In this case, you have a particularly large magnetic field. So the proposal is that if you were to realize two molecules or atoms like that in this kind of a superradiant, subradiant state, you can get actually magnetic functionality. You can even think that you have a more of a tetramer type of situation. In all of these cases, if you were to now put a magnetic transition in there, for example, you know that some rare earth ions have magnetic dipole transitions, which are usually extremely weak, you manage to have a Purcell effect because of this magnetic field that you have here, and you would be able to enhance that magnetic transition by orders of magnitude. So this is something interesting, but somewhat difficult to make materials like that, but that's as far as I could go. But now we're really talking about two atoms or molecules that are only a few tens of nanometers apart from each other. What we have been doing over the past nearly 10 years now in the group is try to get the similar type of functionality, but by having molecules that are not so close to each other. That is, they're actually sitting at much larger distances than something like a wavelength, but nevertheless, they communicate via a common photonic mode. And the simplest way to do this would be to have a one-dimensional bus. So if you could put a whole bunch of molecules and couple them all to one waveguide and force them to all emit into this one waveguide, then you can do the calculation, and this is basically kind of the type of thing that Derek was talking about yesterday. If you confine this to 1D, then you immediately get to a regime of multiple scattering, and so you can explore a kind of a rich phase diagram. You can have Bragg states if they're in a periodic kind of arrangement, but you could also put them in a disorder way, and then that would give you all kinds of fun things like local states, or if you put them very close to each other, then they shift each other and separate from the crowd and all of that effect. So we've looked at this a little bit. I mean, this is a classical calculation, but it really just captures the essence of the photonic modes. And the idea is to try to realize things like that, and that's not very simple in the experiment. So what we have done is we can now, as I showed you in a way already before, make waveguides and couple light into this waveguide and put molecules around this waveguide, and these molecules couple evanescently to the waveguide. And in a way, again, I showed you already a graph like this before. If you couple light in here and couple light out on the other grating and just look at the intensity, then you see all these dips. Each dip is telling you that there was one molecule that scattered the light out. So this looks like, the way to go. But of course, you see that the dips that we have are of the order of a few percent. And if you really want to have a kind of a cooperative effect, these dips have to go more towards 100%. Otherwise, you quickly kind of lose all your interesting effects. So the question is, how efficiently can you actually make a propagating photon interact with one of the molecules or one atom? And this is a very old problem. And again, Derek has already given you the answer. The cross-section of a single two-level system is very well known. It's essentially lambda squared divided by 2. And that makes it very hopeful to be able to have a very good interaction efficiency, because you can confine light down to something of the order of a lambda squared divided by 2 if you simply think that that's the definition of a cross-section. So that's kind of what it means. We try to do this already. Now, this is not in chronological order. This was actually kind of our fascination in the early 2000s to try to see how we can do this. And the reason was partly that all the single molecule work and the single quantum dot work and the NV centers and all of this that was done prior to this work in 2007, they all used fluorescence detection. That is, you were looking at detecting a single quantum emitter, but you're not really to keep preserving the coherence of it, because as in the case of molecules, you excite, but then you look at redshifted fluorescence, and that's for detection kind of technical advantages. But what I've shown you just before was dips. When you see dips, you're doing a resonant kind of coherent interaction. You're not looking at a redshifted fluorescence, which is by definition not giving you any phase information. So we kind of wanted to do this experiment in the early 2000s, and we ended up first calculating a little more carefully, and this is, again, a classical calculation, but it captures all the photonic aspects of things. And in this calculation, you take the vectorial nature of the electromagnetic field of light and say, okay, what happens if I send that onto a point dipole? And you can show that if you can manage to put your incoming photon in a dipolar mode, that mode has a chance of interfering perfectly with the radiation of the point dipole, and therefore you can get a perfect interference, destructive interference in the forward direction, which means that all your light would be reflected completely. So in practice, if you start with a plane wave and focus it with the highest numerical aperture that you can find, you still can get a very good dip of the order of 80–85%. Now, the kind of things that that we do in the lab typically bring us to something of the order of 10%. And this is some of the earlier data that we took. You see here that it goes to about 12%. We had to learn how to do this experiment in the cryostat, that is how to focus light as tightly as we can. So we kind of rigged up our own microscope objective to give us a high numerical aperture, but then the experiment worked immediately. So you're sending light and then look in transmission, and when you become resonant with one molecule, you get a dip. There's no lock-in or anything. This is really what you would see with naked eye. You would see that there's 10–20% drop of light. And by doing this kind of what I can't call that a strong coupling because that's reserved for cavity QED context, we like to call that efficient coupling. By doing this efficient coupling, we were able to study many, many things, especially getting few photon nonlinearities on a single molecule, which of course, always requires more efficient coupling of light. But whatever you do, you see here that we're not getting anywhere close to 100%. And in a way, the reason for it is that we don't have a two-level system. We do have the vibrational levels of the molecule. The molecules that we're using typically have something of the order of 30 to 50 atoms. And if you do your simple back of the envelope calculation, you see that you expect somewhere between 100 and 150 vibrational modes. And this is indeed something that you can measure in the lab. There are a whole bunch of vibrational modes associated with the ground state of the molecule. At the very end, I'll say something about this again. But for this experiment, this is a little bit of a nuisance because it provides a leaky channel. All of these modes are very short-lived. So it's basically a decoherence kind of channel. If you really want to just do experiments on this two-level system, this is bothering you. And this is, in the molecules that we have, it's already actually not bad. That is, you have something of the order of 30% of the light coming down the main channel, and only about 70% goes around like that. But it is not one. And indeed, if you want to go back and be more realistic, then you see that the cross-section that you have, the ideal cross-section, has to be modified by a factor that tells you how realistic this system is. So the question is, how can we go further? And the answer is kind of clear in the quantum optics community, namely use cavity QED. That is, try to enhance this transition so that this becomes a lot faster than this one, so that this ratio becomes closer and closer to 1. And for doing that, we had to put the molecule in a cavity. And so when you put the molecule in a cavity, keeping this concept of cross-section, then what happens is that light comes, but it bounces back and forth, and every time that it bounces, you have a sigma over A probability of interaction, but you enhance this by the finesse. But in practice, you lose in a cavity compared to that tight focusing that we had, because in a realistic cavity, your mode area is larger than we can when we focus down to the diffraction limit. So the figure of merit that you have is the finesse that helps you and the mode area that works against you. If you work out this ratio, you see that it's exactly the same thing as Q over V that you're familiar with from a Purcell factor or the cooperativity. Either way, what you really want to do is you want to have a Q that is high and try to make the mode volume as small as possible. Making the mode volume smaller is quite advantageous. This is where we're in a completely different regime than, for example, the experiments that Tobias showed, in the sense that we try to work with a slightly lower Q, but also much smaller mode volume. The smaller mode volume from a practical point of view is good because we're working in a cryostat, and we don't want to rely on Qs that are too high because the stabilization becomes a lot more difficult. But also, if you want to increase your bandwidth, you don't want your Q to be so high. So we put a lot of effort from the early days. I mean, this is a project that has been going on for more than 10 years now, slowly. We made sure that we go via a route that allows us to make a very small mode volume cavity. And the way to go was to bring a curved mirror close to a flat mirror and then put our crystal with all the molecules on the flat mirror. This is just kind of a practical way of going about it. And we're putting these mirrors at the end of either an AFM tip or a fiber tip. In both cases, we use focused ion beam milling to make a radii of curvature that are particularly small. You might know this type of thing also from the pioneering work of Jakob Reichel, but they use CO2 lasers, and having a wavelength of 10 microns, you can never really get super small radii of curvature, but with focused ion beam milling, you can get down to a couple of microns. Either way, you have to then send your mirror to be coated so that it becomes highly reflecting, and then afterwards you have a game, you have a cavity, and again, this kind of worked pretty much right away once we put all these things together. This is an example of some of the early results. You see that the empty cavity in transmission would have a resonance and in reflection. The typical kind of cavity line width is of the order of, let's say, a couple of gigahertz, right? Remember that the molecule has a line width of a couple of tens of megahertz. So the cavity is much broader than the molecule. So the Q is not that high. But now if you couple one molecule to it, you see that there's a clear signal of completely changing the transmission or reflection of the cavity on resonance when you couple your molecule to it. And that was obtained for these values of Q or finesse. Now we could push this a little more right after that to enter the strong coupling regime. And again, if you look at an empty cavity, this is a resonance that we have, and in the time domain you have what you expect, which is this exponential decay. But when you couple a molecule to it, you have your Rabi splitting, and then you see that we have just the onset of a Rabi oscillation in the time domain. If you want to do better, then we have to improve the Q, and this is kind of what we're doing right now. But there's a number of interesting things to do already with the regime that we have, so that's why we're not much farther into the strong coupling regime yet. With the system that you see here that is entering the strong coupling regime, we are already in a pretty deeply nonlinear regime, and with that, we could do a first kind of simple, fun experiment where we do a kind of a photon switching. Now we're taking two laser beams. They're both very weak. We have one molecule that is resonant with the cavity, And now we can use one laser, which we call pump, but it's really just very weak, just as weak as the probe. And we make a detuning between the two of about 300 megahertz. And basically what you see is that whether the pump has something of the order of 1 photon in it or not, switches the transmission of the cavity completely from 0 to 100%. So this is a simple kind of nonlinearity that has to do with this intrinsic nonlinearity of a two-level system that you have, but it shows that you can play these games. All right, this is in an open cavity, but what we wanted to do was to have a one-dimensional bus and go back to the waveguides. So I'm going to tell you in the next couple of minutes about that experiment. You see here that we have a waveguide, but now we need a cavity, and our cavity is going to be a micro disc. This is a micro disc. It's all built on titanium dioxide technology. So it's a micro disc with a diameter of the order of 6 microns, and that's why the free spectral range is quite large. So this is the mode of the cavity that we take. So as far as the circuit is concerned, you can couple light in here, and then the light will circulate in the resonator. You can pick it up here, but then if there is some scattering, you can also watch it here. Right, so then we put, the contrast is not that good, but you might recognize that I've now put molecules on top. So again, I've sprinkled molecules on top, and now these molecules can couple evanescently to the mode of this microdisc, and this is the one example where the one molecule is coupling extremely well to this resonator. The Q of these resonators is lower than the open cavities that I showed you before. You see here that the line width is in the range of a couple of tens of gigahertz instead of a couple of gigahertz. But what we also have on that circuit, which wasn't clear on the previous slide, but I'm emphasizing it here, are microelectrodes that allow us to Stark tune our molecules at will, because again, remember that these molecules don't come at the same frequency, and if we want to get a cooperative effect, we want to be able to tune them to the same frequency. And so here is a kind of the paper that is on the archive right now. What happened? Right. That is on the archive. Joachim, I'm putting a little advertising for your network. This is the microdisc now. We're zooming into it. And this is a story of two molecules. One of them happens to be here and the other one here. And we can actually watch them because we have a microscope image and we can localize these two molecules. And so on the drop port, this is the extinction of one molecule. This is the extinction of the other one. And this is the sum of the two. And there's an interferometer that is built in. And that shows that this molecule has this signal and this one the other one. So you see that the phases are completely different. These two molecules happen to be at a distance to have a phase shift of equivalent to something like a pi over 2 difference. And that kind of explains this. So I'm going to basically just flash this as an appetizer. So we're coupling two, basically what we're watching is the interference of light scattered from two molecules at the same time. But the coupling of each molecule to the resonator is not enough yet. It's just at the border for the two molecules to actually couple to each other. So right now, they're both independently coupling into a common mode, and we're capturing all of that. Just to finish, I show you a very, very new result from, again, back to the other experiment, where you see that we're now also in that experiment, we're coupling several molecules to the same mode of the cavity. You just had to learn how to put more molecules in this type of a crystal. And we're now excited to actually try to get all of these guys to communicate with each other. And if you have particular ideas, we're happy to talk to you from a theoretical point of view. What I didn't tell you about, but we're very excited about, and we're going to spend a lot of time on it in the next 5 to 10 years, is to take advantage of these vibrational degrees of freedom. And we think that this is actually a very valuable quantum resource that the molecule has. The molecule in this way, the way we look at it, is a natural optomechanical system or a quantum optomechanical system, because you have optical transitions and you have mechanical degrees of freedom, and they're all wonderfully coupled with each other. And we just have to learn how to make these vibrational levels live a little longer, and that's kind of what we're working on. And with all of the things that I told you about regarding this more quantum efforts, I want to tease many of the young people and convince you to leave quantum optics and go do biophysics. And this is kind of my new passion. This is a new center that we're opening in a few months in Erlangen, where we try to do basic research at the interface between physics and life sciences. Thank you very much.